It is permissible to have a feeder operating at 13,800 volts within an existing office complex, contingent upon strict adherence to all relevant electrical codes and safety regulations. The National Electrical Code, specifically Article 300.3b, mandates that electrical conductors rated at 1000 volts or higher must be installed within metal raceways. Therefore, the utilization of rigid conduit for the exposed segment of the feeder aligns with these requirements. Primary fuses, however, do not meet the definition of a service disconnect as outlined in the NEC. A service disconnect is designed to isolate all ungrounded conductors of a service at its point of entry. This is to provide protection and facilitate maintenance within the electrical system. In this scenario, the primary fuses are situated within a vault and their primary function is to protect the transformer. They do not disconnect all ungrounded conductors of the service and are not considered to be a service disconnect. A knife blade disconnect switch, when properly sized and installed, has the potential to function as a service disconnect. It should be positioned in an accessible location outside of the vault and clearly marked as the service disconnect. Additional factors must be considered. Firstly, a qualified electrician should inspect and approve the entire electrical installation. Secondly, the facility should maintain a well-documented safety program, including comprehensive training for employees who may interact with or be in proximity to the high-voltage feeder. Thirdly, proper grounding and bonding techniques are essential for ensuring electrical safety. Fourthly, conduct routine maintenance and testing on the electrical system to maintain its reliability and safety over time. Metal raceways, as specified in the NEC, provide a grounded enclosure for conductors, which helps to minimize the risk of electrical shock and fire. The NEC provides specific requirements for the type and size of raceway to be used, depending on the voltage and current of the conductors. Article 314 covers outlet, device, pull and junction boxes, conduit bodies, fittings and handheld enclosures. These should be suitable for the environment and application. Selecting the proper type of rigid conduit is crucial. Options include rigid metal conduit, intermediate metal conduit, and rigid polyvinyl chloride conduit. Each type has specific applications and limitations outlined in the NEC. The size of the conduit is determined by the number and size of the conductors it will contain, as well as the NEC fill requirements. The NEC specifies the maximum percentage of the conduit's cross-sectional area that can be occupied by conductors. Proper installation techniques are critical for ensuring the integrity of the conduit system. This includes using appropriate fittings and supports, and ensuring that the conduit is properly grounded and bonded. Grounding and bonding create a low impedance path for fault currents, which helps to treat circuit breakers and ground fault protection devices, minimizing the risk of electrical shock. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting different metallic parts of the system together. The NEC provides detailed requirements for grounding and bonding in Article 250. A service disconnect must be readily accessible, meaning it must be located where it can be easily reached in case of an emergency. It should be clearly labeled to indicate its function. The disconnect must be capable of interrupting the maximum available fault current at the service entrance. A knife blade disconnect switch is a type of manual disconnect switch that uses a hinge blade to make or break the electrical connection. While it can serve as a service disconnect, it must be properly rated for the voltage and current of the service. The NEC also requires that the disconnect be lockable in the open position to allow for safe maintenance and repairs. The primary fuses protect the transformer from overcurrent conditions. They are typically sized to protect the transformer's insulation and prevent catastrophic failure. The size and type of fuses are determined by the transformer's nameplate rating and the NEC requirements. While the primary fuses provide protection for the transformer, they do not meet the requirements for a service disconnect. A service disconnect must disconnect all ungrounded conductors of the service, while the primary fuses only protect the transformer. An effective safety program includes regular training for employees who may come into contact with electrical equipment. The training should cover topics such as electrical hazards, safe work practices, and the proper use of personal protective equipment. Employees should also be trained on how to respond to electrical emergencies, such as electrical shocks and fires. Regular maintenance and testing are essential for ensuring the continued reliability and safety of the electrical system. This includes visual inspections, insulation resistance testing, and ground impedance testing. Any problems identified during maintenance or testing should be promptly addressed. Insulation resistance testing measures the resistance of the insulation surrounding the conductors. This test can help to identify insulation degradation, which can lead to electrical shorts and shocks. Ground impedance testing measures the impedance of the grounding system. This test can help to identify problems with the grounding system, which can increase the risk of electrical shock. Consider also the ampacity of the conductors. The ampacity of a conductor is its current carrying capacity, expressed in amps. The NEC provides tables that list the ampacity of different types and sizes of conductors based on their insulation type and installation conditions. The ampacity of the feeder conductors must be sufficient to carry the load served by the transformer with appropriate overcurrent protection. Also consider voltage drop. Voltage drop is the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Consider harmonic distortion. Harmonic distortion is the presence of unwanted harmonic frequencies in the electrical system. Harmonics can be generated by nonlinear loads such as electronic devices and variable frequency drives. Excessive harmonic distortion can cause equipment to overheat and can also interfere with the operation of sensitive electronic equipment. Also consider surge protection. Surge protection devices protect electrical equipment from voltage surges which can be caused by lightning strikes, switching operations, and other events. Surge protection devices should be installed at the service entrance and at sensitive electronic equipment. Furthermore, consider coordination of overcurrent protection. Coordination of overcurrent protection ensures that the overcurrent protective devices, such as circuit breakers and fuses, are properly sized and coordinated to protect the electrical system from overcurrents. Coordination studies should be performed to ensure that the overcurrent protective devices will operate in the correct sequence to isolate faults and prevent unnecessary outages. Arc flash hazard analysis should be performed to determine the potential arc flash hazards associated with the electrical system. Arc flash is a dangerous electrical explosion that can cause serious injury or death. The arc flash hazard analysis should identify the potential arc flash boundaries and the personal protective equipment that is required to work safely on the electrical system. Labeling is important. All electrical equipment should be clearly labeled to identify its function and voltage. Labels should also be used to warn of potential electrical hazards such as arc flash. Documentation should include complete and accurate documentation of the electrical system, including drawings, specifications, and maintenance records. This documentation should be readily available to qualified personnel. The applicable codes and standards are the NEC, as well as any applicable state and local electrical codes. These codes and standards provide the minimum requirements for the safe installation and operation of electrical systems. Regular inspections are important. Regular inspections of the electrical system should be performed by a qualified electrician to ensure that it is in compliance with applicable codes and standards and that it is operating safely. Also consider the environmental conditions. The electrical equipment should be suitable for the environmental conditions in which it is installed. For example, equipment installed in damp or corrosive environments should be appropriately rated for those conditions. And consider energy efficiency. Energy-efficient electrical equipment should be used whenever possible to reduce energy consumption and save money. This includes using energy-efficient transformers, motors, and lighting. Finally, worker safety is paramount. All work on the electrical system should be performed by qualified personnel who are trained in safe work practices. The electrical system should be de-energized before any work is performed, and appropriate personal protective equipment should be used. Remember, a 13,800-volt system presents significant hazards. Only qualified and trained personnel should work on or near this equipment. Ensure all safety protocols are strictly followed at all times. Grounding and bonding are critical for safety. Improper grounding and bonding can lead to electrical shock hazards. Ensure that the grounding and bonding system is properly installed and maintained. Overcurrent protection is essential for preventing damage to equipment and minimizing the risk of electrical fires. Ensure that the overcurrent protective devices are properly sized and coordinated. Regular maintenance is crucial for ensuring the continued safe and reliable operation of the electrical system. Neglecting maintenance can lead to equipment failures and increase the risk of accidents. Always follow lockout/tagout procedures before working on electrical equipment. This will prevent the equipment from being accidentally energized while work is being performed. Use appropriate personal protective equipment, including gloves, safety glasses, and arc-rated clothing, when working on or near electrical equipment. Be aware of the potential hazards associated with high-voltage electricity, including electrical shock, arc flash, and arc blast. If you are not qualified to work on electrical equipment, do not attempt to do so. Contact a qualified electrician. Furthermore, be familiar with the location of emergency shut-off switches and procedures. Know how to energize the electrical system in case of an emergency. Keep the work area clean and free of obstructions. This will help to prevent accidents and ensure that you can work safely. Use insulated tools when working on or near electrical equipment. This will help to protect you from electrical shock. Never work alone on electrical equipment. Always have someone nearby who can assist you in case of an emergency. Report any unsafe conditions or practices to your supervisor or safety officer. Continuous monitoring of the electrical system can help to detect problems early and prevent them from escalating. Consider using a power quality meter to monitor voltage, current, harmonics, and other electrical parameters. Conduct regular safety audits to identify potential hazards and ensure that safety procedures are being followed. Stay up to date on the latest electrical codes and standards. The NEC is updated every 3 years, so it is important to stay current on the latest requirements. Participate in continuing education courses to improve your knowledge and skills in electrical safety. Consider seeking certification as an electrical safety professional. This will demonstrate your commitment to electrical safety and your expertise in the field. Maintain a healthy respect for electricity. It is a powerful force that can be dangerous if not handled properly. By following these safety tips, you can help to prevent electrical accidents and ensure a safe working environment. Remember, safety should be a prime consideration when dealing with high-voltage systems such as a 13,800-volt feeder. Regular training and adherence to the NEC are paramount for the safety of personnel and the longevity of the electrical system. Employ qualified personnel, conduct regular inspections and audit, and document everything for future reference. A proactive approach to safety and maintenance is always the best approach when dealing with high-voltage power systems. When installing a knife blade disconnect switch, ensure it is rated for the appropriate voltage and current. The interrupting rating of the switch must be sufficient for the available fault current at that location. The switch should be clearly labeled as the service disconnect and be readily accessible in case of an emergency. The switch should be installed in a weatherproof enclosure if it is located outdoors. The switch should be lockable in the open position for safety during maintenance and repairs. The switch should be inspected regularly to ensure that it is in good working condition. The blade should be clean and free of corrosion, and the contacts should be tight. The switch should be operated periodically to ensure that it is functioning properly. If the switch is damaged or worn, it should be replaced immediately. Never attempt to repair a knife blade disconnect switch. Always replace it with a new one. When working on or near a knife blade disconnect switch, always follow lockout/tagout procedures. This will prevent the switch from being accidentally closed while work is being performed. Use appropriate personal protective equipment, including gloves, safety glasses, and arc-rated clothing. Be aware of the potential hazards associated with knife blade disconnect switches, including electrical shock, arc flash, and arc blast. If you are not qualified to work on knife blade disconnect switches, do not attempt to do so. Contact a qualified electrician. Always follow the manufacturer's instructions when installing and operating a knife blade disconnect switch. Consider the coordination between the primary fuses and the knife blade disconnect switch. The fuses should be sized to protect the transformer, while the disconnect switch should be sized to interrupt the available fault current. Proper coordination between these devices is essential for ensuring the safety and reliability of the electrical system. Ensure that the knife blade disconnect switch is properly grounded and bonded. This will help to prevent electrical shock hazards. The grounding and bonding system should be inspected regularly to ensure that it is in good working condition. If the grounding and bonding system is damaged or worn, it should be repaired immediately. Use appropriate tools when working on or near a knife blade disconnect switch. This will help to prevent damage to the switch and ensure that you can work safely. Never use excessive force when operating a knife blade disconnect switch. If the switch is difficult to operate, contact a qualified electrician. Keep the area around the knife blade disconnect switch clean and free of obstructions. This will help to prevent accidents and ensure that you can access the switch quickly in case of an emergency. Regularly inspect the knife blade disconnect switch for signs of overheating. Overheating can be caused by loose connections, corrosion, or overloading. If you suspect that a knife blade disconnect switch is overheating, contact a qualified electrician immediately. Ensure that the knife blade disconnect switch is properly rated for the environment in which it is installed. If the switch is installed in a damp or corrosive environment, it should be appropriately rated for those conditions. Regularly inspect the knife blade disconnect switch for signs of damage or wear. If the switch is damaged or worn, it should be replaced immediately. Never attempt to repair a damaged knife blade disconnect switch. Always replace it with a new one. When replacing a knife blade disconnect switch, always use a switch that is rated for the same voltage and current as the original switch. Using a switch that is not properly rated can be dangerous. Ensure that the knife blade disconnect switch is installed in accordance with the NEC and all applicable state and local codes. This will help to ensure that the switch is installed safely and correctly. Always follow the manufacturer's instructions when installing and operating a knife blade disconnect switch. The manufacturer's instructions provide important information about the switch's operation and maintenance. Keep a copy of the manufacturer's instructions readily available for future reference. If you have any questions about the knife blade disconnect switch, contact a qualified electrician. A qualified electrician can provide you with the information and assistance you need to ensure that the switch is installed and operated safely. And remember, the purpose of a service disconnect is to provide a means of quickly and safely disconnecting power to the entire facility in the event of an emergency or for maintenance purposes. It is a critical safety component of the electrical system and should be treated with the utmost respect. In summary, when dealing with a 13,800 volt feeder and associated service disconnects, prioritize safety, adherence to codes, and the use of qualified personnel. Regular maintenance, thorough documentation, and continuous monitoring are essential for maintaining a safe and reliable electrical system. Always err on the side of caution and seek professional guidance when in doubt.